All right. So let's start officially. Hello, everyone. Welcome to episode 23 of Warsaw.AI meetups. My name is Paweł. I'm one of the organizers, and I'm the founder and CEO of the Quantum AI Foundation. We are the organizers of this meetup together with Ideas NCBR. Before we start, we would like to thank our partners and sponsors, Allegro Tech, for hosting us here for the next time, and Data Art. We have several participants from Data Art today, and Data Art also supports our weekly newsletter, Warsaw AI News. So we also encourage you to subscribe if you haven't done it yet. And today we have pleasure to host three, or actually four, great speakers, because one talk will be given by two speakers. So first, Sebastian from Ideas NCBR will tell us about scaling laws for fine-grained mixture of experts. Then we'll have two gentlemen from TCL Research Europe. They will tell about practical low-rank decomposition for large language models. Łukasz and Michał are already with us. And finally, we'll have a speaker from our host today, from Allegro, Aleksandra Chrabrowa. She will join us a bit later today, hopefully, and she'll tell us about dense retrieval for Allegro search engine. After the talks, there will be the after party with sushi, so we hope that you'll stay with us for networking. And I think we can start. So Sebastian, if you're ready, we can start.
Okay, so thank you for the introduction. It's my pleasure to talk to you all about my research work, or our research work on scaling laws for fine-grained mixture of experts. So a few words about me. I lead a small research team at Ideas NCBR, and we focus on LLM efficiency, mainly mixture of experts, but also other topics as well. But this presentation in particular is about mixture of experts. First things first, let's talk briefly about motivation of our work. So LLM's popularity is increasing, as you probably have noticed, and so is the cost of LLM training and LLM inference. Mixture of experts, however, offers more efficient training of LLMs, and therefore are getting scaled and improved. And we know, for example, that most recent flagship models use mixture of experts in some capacity. Despite that, previous academic literature actually predicted dense transformers to surpass mixture of experts at some scale. What was surprising to me and counterintuitive, but here in this work we refute that claim or show the assumptions made, which I do not agree with. So our goals in this work were twofold. First is to improve the architecture of mixture of experts and also better understand the scaling properties of mixture of experts and LLMs with MOE. So a little bit of a background in mixture of experts and in transformers. So here you see the standard transformer architecture diagram. Most of parts here we do not need to understand for the purposes of this presentation. The most important part for MOE is those blocks in red circle, because the MOE block replaces the feed-forward layer in transformer, and this is even in vanilla transformer where most of the model parameters reside. So MOE replaces that, and it doesn't really have much of an interaction with other parts of the transformer. So how does feed-forward work? We don't need to get into much detail about inner workings of the feed-forward. From our perspective, it's a function, MLP usually, which processes the whole sequence of the tokens by processing each and every token independently from one another. And all those tokens are processed by the same MLP, by the same function with the same parameters. So pretty straightforward. How can we improve on that? Well, we can actually have multiple variants of this feed-forward layer, with each variant being called an expert. And then with multiple variants, they can specialize in processing different tokens. And during inference, each token may be routed to the most relevant expert for processing and get output from this most relevant expert. So we can have more knowledge stored in the model despite using the same amount of computation as in the base model. So we also have routing, of course. Usually routing is done by a small multi-layer perceptron again, or maybe a single layer, which assigns experts to tokens. The cost of routing is small in general, but it has to be taken into account, especially as the number of experts increase. So this is the all of the background in transformers MOE we need for this presentation. So what then is granularity or fine-grained mixture of experts? Well, in standard mixture of experts, like implicitly, we just use multiple variants of the original feed-forward layer, and like on the diagram, on the left diagram, we use a single variant for each token. But we could actually keep the total number of parameters and the approximately the same amount of computation if we split each expert into, let's say, 2 parts or into multiple parts, and route each token into appropriate number of experts to keep the total computation constant. So basically, we have the model of the same size, costing with the same cost as, or approximately the same cost as before, but it has more flexibility. What parameters and what weights of the model it can choose, right? The cost increases only slightly because we have more routing to do essentially. So that's great. The model has way more flexibility, but the cost of routing increases, which is all good. But then we have to decide what is the optimal trade-off between those 2 things. So this is we have to use some definitions, like let's define granularity as the size of the base feed-forward layer divided by the expert size. So basically, in how many experts compared to the baseline transformer we split original feed-forward to get more granular experts. And then instead of using just a raw number of experts to compare model sizes, we can define the expansion rate as the number of total parameters divided by the number of activated parameters used for a single token. And traditionally and implicitly, I must add, granularity was basically equal to 1, and expansion rate was equal to the number of experts. So we had to make those definitions on our own. We can see from preliminary results that granularity really helps. This additional flexibility helps the model, and with each increase in granularity, the model achieves better loss, but with some diminishing returns. However, we have to somehow quantify how much of a gain do we get, and especially we are interested in how much of a gain we will get at large model scale, right? So so usually to get those optimal trade-offs, we can use scaling loss. So a little bit of a background into scaling loss. There was this famous work from OpenAI, scaling loss for neural language models, which not only showed that the model will improve if you just feed it more data and more parameters during training, but also that it improves predictably. Like with appropriate log-log scale, there is basically a straight line that you can draw on the chart showing the relationship between the model quality and amount of data or number of parameters. So that was paper from OpenAI. Those scaling laws were later refined by DeepMind. So you may know them as chinchilla scaling laws. And in that work, they derived a formula describing the loss landscape, like the dependence of loss on the number of parameters and data points. And with such an equation, we can just fit coefficients in this formula to our experimental results. And if we have this formula with coefficients, we can then calculate compute optimal hyperparameters for our model, which is important if you want to scale the model up. Those two works that I mentioned, however, only talked about dense transformers without MOE. And for MOE, DeepMind released the paper Clark et al. That modeled the loss function, although with a fixed data set size. Like you can notice that the number of tokens D is not present in as an argument to this function. So you would have to fit those coefficients for a given data set size. And this importantly does not allow to calculate the optimal data set size, obviously. And in this work, there was this conclusion that I mentioned in the introduction that at some point, mixture of experts seem to underperform a dense model despite having more parameters and equal cost of training or inference. And this point, as predicted by this work, should happen around 1 trillion parameters in the model. We will go back to this later. But for now, we want to derive scaling laws for fine-grained MOE ourselves. How do we do that? So, like formally, we want to study the relationship between parameters like loss and final perplexity of the model, which is basically loss, and the number of parameters and the training tokens and the granularity level that we use. In our experiments, we fixed the expansion rate. We focused on E = 64, which was popular when we started around probably a year ago or so. And we provide separate feed for different expansion rates. So we want to first, before even we feed coefficients, like we want to know what should be the equation that we use, right? So I will present to you a very short version how we do that. Like this is explained in more detail in the paper. But in general, we have noticed that for constant data set size and number of parameters, the dependence of loss on granularity is described well by power law. And for constant granularity, the loss landscape is described pretty well by original chinchilla scaling laws, just with different coefficients. And we one by one checked where should we put like in what factors of the equation we should inject the power law of granularity into the chinchilla scaling law, and we ended up with this formula as shown. So with for mathematical formula derived, we can just fit coefficients in this equation based on experimental data. So we did that. We ran over 100 experiments with different values of n, d, and g, with models up to over 3 billion parameters total, although up to 100 million or something around that active parameters. And we run additional sweep of dense transformers as well to compare their performance with MOE, like to answer the question if MOE will overperform at any scale the dense models or not. With all those experiments, we have fitted the coefficients, but the coefficients on their own do not tell us much, of course. But we could see that with those coefficients, the data fits pretty well. The experimental data that we had marked with dots fitted the scaling laws that we derived pretty well, with our predictions marked in with dotted lines. And also, if we validate it by excluding top 20% best performing, so the largest models and the models trained on the longest, and just use bottom 80% of the models as the training set for fitting coefficients, we can see that also we get good predictions for larger models. So it seems that scaling laws extrapolate to larger and larger models, just like previous works on scaling laws. Okay, with all that, we can think about optimal allocation of compute for the training. So basically, we want to minimize this loss function, keeping constant the training budget, with flops based on n, d, and g being also a function that we can calculate. And when we plotted, when we compared the dense model to MOE, or optimal scaling of dense model to optimal scaling of MOE, we can see that basically at any point the dense model will have a worse model quality with the same training budget. And we can see that for commonly used models, like commonly used open source models like 1B or 7B active parameters, the optimal granularity should be around 16 instead of just 1 implicitly used before. Okay, so what amount of difference in computation are we speaking about actually? So if we see the cost, the relative cost of training a dense model or the MOE model with not optimal granularity, we can see that the dense model in general will be over 10, 20 times more costly than optimal MOE scaling. With this difference actually increasing when we scale the training budget, when we increase the training budget, and MOE with implicitly used granularity of 1, like in works before, results in around 2 times larger cost for the training. Okay, so we can see that at any budget, basically, MOE model surpasses dense model at any scale. So what's up with that work from DeepMind, Clark et al.? So we could see that with actually a small data set size relative to the model size, a dense model actually is better, both according to the Clark et al. And according to our own scaling laws. Like if you just assume the constant dataset size and only scale the model up, the dense model will outperform MOE at some point. And we also get very similar threshold point. Like I think Clark et al. Got around 1 trillion parameters as a crossing point where dense model will start surpassing MOE, and we got around 2 trillion. But it is very important to know that this regime is entered if you're really under-training the model. Basically, you have around 100 times fewer tokens than suggested by Chinchilla, like optimal scale, optimal scaling laws. So you're in under-trained regime, and in practice, like compared to the theory, in practice you are you want to enter overtrained regime where you use 10 or 100 times more tokens than parameters compared to the Chinchilla scaling laws. For example, like Llama does. So it is true that dense model in some situations will surpass MOE, but it is basically never practical to do so because nobody does undertrained models because they are most costly for inference. So yeah, this explains the results by Clark et al. Okay, what are practical insights of their work? So first of all, the standard value of granularity 1 is in practice never optimal. Also, granularity should gradually grow as we increase the model size. And importantly for us, MOE models will continue to be better than dense models at basically any scale. Also, it's worthwhile to note that implementation is important, especially with granular models, because this is a slightly different approach than we have traditionally with MOE. And for example, ScatterMoe was a nice implementation that came out after our work. And they speed up also wall clock time to match the expected theoretical flops for MOE, especially when granularity is increased. So this is not our implementation, but it was based on our work, like after our work. Okay, so to conclude, MOE will always be more efficient in language modeling, and granular MOE actually are getting adopted, like with bigger and bigger models getting released using fine-grained mixture of experts. And we expect, in general, further scaling and granularization, should I say, of MOE models. So thank you for the attention, and I'll welcome any questions if we have time for that.
Thanks, thank you. I guess we have time for questions, and I can see the first questions.
Thank you for a very interesting presentation. I'm no expert in the case of language models, especially from the compute side. So I just wanted to find out, how do we control for the choice of hyperparameters, and can we be actually sure that some model performs in some way because we didn't, for example, choose some weird learning rate with a weird scheduler or something?
Okay. So in general, to compute scaling laws, like you fix and you have to use some reasonable scaling of different parameters. Like you not only need to have a certain number of parameters, like marked by n, but also like proper width to depth ratio of the transformer. But this is in general described in literature in other works, how we can approach it and how we should do that. So yeah, it is important to do. I think we did a proper job in our experiments doing that, but this is this is a problem encountered by basically all scaling lossly works. So I hope I've answered your question properly.
Okay, good. Do we have more questions, Sebastian?
You mentioned this DeepSeek, Quen, and the BarX papers, and they used shared experts as well. So, what's the? Have you been investigating like the optimal ratio of shared to like standard experts and so on?
We unfortunately haven't explored that. That would be interesting. It's worthwhile to note, however, that shared expert is like existence of shared expert is basically equivalent to like standard feed-forward layer running in like parallel to MOE. We have while we have not run experiments with parallel shared expert, basically we have run experiments with alternating MOE and standard feed-forward, so that would be like shared expert, only alternating instead of running it in parallel, and it seems that well, granularity still helps. I'm not sure how much, like compared to standard approach.
I wanted to ask you, what's your take on the relationship between those topics and pruning? There was this paper a few years back, lottery ticket hypothesis, right? When they showed that you can train a over-parameterized model, but you're best off if you prune like 90% of the parameters from that. But the clue insight was that they done it after the training, right? So you had to do training in this like super over-parameterized regime. So I wanted, so if I understood you correctly, here you start the training with like those different experts, right? So yeah, I just wanted to pick your brain on what's the like philosophical relationship between those two themes. Okay,
about pruning. So it seems to me that pruning usually, when it works, it saves more on like memory cost for inference and for storing the model, and not so much on the actual computation cost during inference, unless you use structure sparsity, but structure sparsity really lowers the model quality, as far as I know, in practice. So I would say those are pretty different techniques in terms of goals, like unstructured sparsity and MOE. When thinking about structure sparsity, like when there is overlap, I think MOE use compute more efficiently, but like they do not save memory on your hard drive, right? So in general, I would say those are pretty different techniques used. Like MOE are used when you have a lot of memory, like when you're running maybe inference on large clusters, large GPU nodes, and pruning you do more often, I think, on end devices, etc. And lottery ticket in particular, like as far as I know, it doesn't really replicate. So like at least as far as I've talked with people like in person, like even people working people with work on LTH, I would say, they also don't believe in a lottery ticket hypothesis. Like it works probably on small models, but not really on large models or large language models. So yeah. I'll be happy to talk and answer more questions after the talk. I'll be available for sure here. So yeah, thank you so much for listening.
Great, thank you once again, Sebastian. Yes, there will be time to ask more questions during our networking part and after party, and now it's time for our next speakers from TCL Research.
Okay, hello. I will be presenting our work on like some of model compression aspects that we have been working on. And first, we will talk about like what is low rank compression, where can you use it, and what's the point. Then we'll talk about like the approach how we use this approach for compressing large language models and also vision models. And maybe later a little bit about from the practical side about the package we developed to make it accessible and easy to use. Yeah, so we're part of a larger team here that we've been doing model compression and model optimization for a long time now, from neural architecture search to pruning to knowledge distillation and so on. So this is like our most recent work, and this the actual low rank compression efforts were also done with like with Krzysiek Tomala, who is here. So yeah, and that's about us, and maybe a little bit about low rank compression, what it is, and where can we use it. So generally, like when you think about low rank stuff, you think of SVD, singular variable decomposition, so which is can be proven to be optimal in some scenarios. Generally, you have a large matrix, and you have a lot of those in large language models, and you want to try to make replace it by two smaller matrices, hopefully with little loss in quality, with little difference in terms of outputs. So yeah, that's the picture. I think tells it all. It's not complicated stuff. So what we do, and what is important to notice, is that the inputs to these matrices in models don't really come from a very let's say uniform or Gaussian distribution. They're very structured, and you have to try to take this into account when compressing these matrices. So SVD can be shown not to be optimal when the input is not let's say uniform distributed in the sphere. So we're much better off taking this into account and coming up with some kind of procedures or algorithms that look into the inputs, outputs, and try to find a better way to create these smaller matrices. So the idea here is to, and we're following like footsteps of the paper that's highlighted here. So the idea is that, yeah, maybe the weights themselves of the models are not essentially low rank, but the outputs and the inputs as well can be. So we'll try to take this into account when we compute this matrices. So given some linear layer, it can be one-by-one convolution, but let's focus on linear layers. What we do is we compute the outputs of this layer, and then try outputs on the, let's say, calibration dataset, which doesn't really have to be that large, let's say 1,000 or 4,000 examples. And then we compute a matrix of eigenvalues and of here, okay, eigenvectors. Eigenvalues are computed, by the way. So if, for example, W, which is our weight matrix, has dim out, dim in shape, this Q matrix of eigenvectors, has the same shape. It's a quadratic matrix of the shape dim out, dim out. So we can then use this matrix to create these smaller matrices. So we will split W into two parts, U and V, where like U will be this, okay, I forgot about the important part here. So there's this R here. R is the rank that we choose, and how we choose it later about it. But when we can slide R up and down to better or worse approximate the original outputs. So when we do this decomposition, we take U to be this Q matrix. Oh, I forgot the transpose part. It should be transposed, but it's not that important. And we take the V matrix to be this Q matrix sliced and fused with W. So in the end, we come up with two smaller matrices. We have a hyperparameter R that we have to choose somehow. And how we do that? So again, I already mentioned that. So choosing the rank for different layers in an optimal way, it's like doesn't seem that easy. Mostly like in the literature at the very beginning, people were doing that just using some heuristics. So in the paper I mentioned, they said, okay, let's try to decompose only layers of linear layers of blocks from certain point, and we're going to choose the same R for like the same compression ratio for all of them. So we decided to do it like something more refined, but still relatively simple. So what we do, okay, we take all linear layers. There's no picking and choosing, like all the linear layers in the model. We run a lot of forward passes, like on this calibration data set, compute these matrices of eigenvectors. And yeah, and we have these matrices, and we have to choose these ranks for all these matrices. So it can be like 200, 400 decisions to be made. And we, as I said, we do nothing complicated, just starting from the last layer. We have a decision to make, and we choose the ratio by carefully trading off the perplexity increase that would result in choosing a smaller rank and the drop in the number of parameters that will happen once we make this rank R smaller. And we have one hyperparameter in the whole procedure, which is basically saying how aggressive we want this decomposition to be. So there are, like, again, as I said, the procedure is like not that complicated, but it has a lot of advantages though, mainly because of its simplicity. And so one thing is like we have been able to run it on a lot of models, and I haven't really seen examples of it not working, because like in the end we replace a linear layer by two linear layers, and from the model side perspective, it doesn't really matter that much. Again, as I mentioned, we do not use any heuristics. We just try to choose somehow. It's not optimal, obviously, but we have some proxy for choosing this rank, and we do not fix any layers that we are going to work on or not. Everything has the same chance of being compressed, let's say. Another like practical advantage, it's very fast to run. It doesn't require much more memory than just running the forward pass. There's one quirk here with computing these eigenvectors matrices. It's usually much better not to do it in float 16, even float 32. It's best to do it in double precision, and it's like from the numerical perspective. It's an insight from the numerical side of things. When we are done with this procedure, then we can do some additional fine-tuning, which really helps for smaller models. Doesn't make too much difference for larger models. I mean, larger, not that aggressively compressed models. And the advantage that another, like, let's say, thing that we really liked about this method is that, like, when you look into the, like, more generally, when you look into the compression literature and algorithms for LLMs, they underperform like really badly the state of the art for computer vision models. Pruning, or let's say, maybe pruning is a good example, because like it's really hard for structured pruning to achieve better results than just taking a smaller model. Which is definitely not the case, at least from our perspective, and we've seen a lot of examples like that for vision models, for smaller models. And we've been able to, let's say, go almost to 50% reduction in the number of parameters without the model collapsing, which is the issue with a lot of other procedures and papers. So they only report results, okay, we go down to 70% of the regional model size. We do not report results for let's say 40 or 50%. And it's usually the reason behind this is that like the model just doesn't work. The perplexity shoots up, and we're in a very bad spot. So given like the procedure and the algorithm we have developed, there are a couple of things that maybe a couple of interesting extensions, and we will be very happy to discuss it with anyone if you want to work on it. So recently, DeepSeek was also mentioned before, but there's this DeepSeek v2 architecture. And if you look into the technical report, it's a very good read, by the way. I strongly recommend it. They do something called multi-head latent attention. And the whole idea is to make the KV cache much smaller by using low rank approximations to compress keys and values of LLMs. Like for those that are not familiar with this stuff, when you run generation for LLMs, you have to store in your memory a lot of data in order not to compute some things twice, thrice, and so on. And there's a strong drive to make this key and values cache much smaller. And there's a way to do that, maybe using our approach, because essentially, maybe there will be a plot later on, but it's not that the ranks of different types of layers are, let's say, more or less the same. So, for example, for LLMs, it's much easier. You can choose very small R for queries and keys, not so small for values, but still you can use that insight and try to work on this key value cache optimization. The problem here is that we are usually taking a pre-trained model, and this multi-head latent attention model, DeepSeek v2 architecture, which is again a fine-grained mixture of experts, by the way, on the NLP side, was trained with this low-rank compression procedure from scratch. So that's a different story here. Okay, and here maybe we'll switch to Michał, who will talk about the results and that we have and so on.
Okay, thank you. So indeed, I will tell a couple of words about applications of a method that Łukasz described. We will start with large language models. And one of the most popular architectures these days is Llama. Well, very, very nice model from Meta. The little downside of Llama is that it has, the smallest model has 7B parameters in version 2, and lately the Llama 3 is 8B. So not everybody is happy that it is this big model, and people try to compress it. And I presented to you results of applications of a couple of methods. The blue line on this plot is our approach, low-rank compression, and the other two is SliceGPT and LLM Surgeon. So on the x-axis, you have the number of parameters, and on the y-axis, you have the score, which is in the case the average of 5 commonly used large language model benchmarks. Yes. So as you can see, if you are willing to sacrifice some of the model quality, you can shrink it to 5B or even 4B. And as you can also see, our method, the blue line, is quite competitive with other approaches, and especially what Łukasz mentioned, we have quite good results for very high compression ratios. The big caveat here that is that these results are after very lightweight recovery fine-tuning with LoRa and on the Alpaca dataset. So for practical application, you could probably do even better if you had bigger dataset and if you put more compute to the problem. Practical consideration, one decomposition takes roughly 1 day on a A100 GPU, including this lightweight fine-tuning. Yes, so as Łukasz mentioned, our method is not limited to single architecture. We can decompose almost any model. So here there is the results, for example, here are the results for Phi2. So as you can see here, it's the difference even for small compression ratios is even bigger. So we do in this case better than sliced GPT. Now we have reduced the size of the model. So what we actually gained. Here in this table, I present you a results of throughput on the RTX 3090 card. This speed up or increase of throughput comes essentially from two sources. Your decomposed linear layers have smaller matrices inside, so that's less flops to compute, so that's a good thing. And second thing is that the composed model takes up smaller GPU RAM. So the more GPU RAM is left for the data, so you can fit bigger batch sizes. So you have fewer flops in the model and more RAM for your data. So as you can see, depending on the quality you wish to sacrifice, you can speed up the model by 30% or even 50%. Yes. And what Łukasz also slightly mentioned, this method can be also a tool to see some inner workings of your model. So here I presented the results for Llama 2 7B decomposed to 5B, and these are the ranks of projection matrices. Yes, so there are 4,000 by 4,000, and they are decomposed in the procedure to something smaller in between. Yes, so this RDeco parameter that Łukasz had on the slide. So if it is, if on this plot you have like one, it means that the matrix was not decomposed at all. So we can clearly see that, for example, key and value projections are decomposed much more aggressively, almost uniformly throughout the whole model. And for example, there are some layers, some blocks, which are decomposed very aggressively in all projections. Like in the end, you can see this layer 28. Yes, so this can give you some insights. For example, if you were to remove some blocks from the model, it could be probably good. It would be good to start from the blocks that have relatively low ranks in decomposition. So this is quite interesting. Okay, so this was about language models. Now we can also apply the same method for vision models. And here I took the two sample models. One is RexNet 100. This is a convolutional model, and it has like 5 million of parameters. And then SwinV2 Tiny, which is this time a transformer model, and it has the full model has 30 million parameters. And here I presented the curves which are obtained by increasingly aggressive decompositions. So as you can see, the raw decomposed models lose quality quite quickly. So on the y-axis you have the standard ImageNet accuracy, and on the x-axis again the size of the model. But here we are lucky because in the vision area it's very easy to have a good data set and good recovery fine-tuning. And after recovery fine-tuning, you can recover a lot of, or you can have back a lot of the lost quality in the decomposition process. So I have put here the information about the final accuracy of this most decomposed model. So we lose roughly 2%. Okay, and then if you have this model decomposed, what did you actually gain? So these are like small vision models, so you can easily deploy them on the phone. So I have run the benchmarks on the TCL phone, just a sample one. By the way, TCL builds a budget phones, so the absolute numbers are not very high. So iPhones, when you have papers that run models on iPhones, the absolute numbers will be much bigger. So for the smaller model, the convolutional nets, the speed up both on CPU and GPU is like 10%, and for this bigger model, we get about around 40 or 30% speed up. So again, on the this gives you whole continue spectrum of models. I showed the results for the most decomposed one, but if you are unhappy about the quality, you can select less decomposed model and have lower speed up at the cost of better quality. Okay, now a little bit about decomposition in practice. We created a little library called PTDeco, which implements the method I mentioned. For now, we use it internally, but it's open source, so you can look it up and see if it is useful for you, and especially if what I showed resonates with your applications, just talk to us afterwards. We'll be happy to hear about your use cases. The main selling points are that the method doesn't need any special treatment, so any special preparation of your model. It should run as is. So the models I showed before were just plain models from team. I haven't done any modifications. I was able to decompose them. We want the models to be easily shareable. The whole library should be also useful in other domains than LLMs and visions. In principle, there should be no problem in making it work in your application. The future aim is, of course, to have a library that will cover a lot of decomposition methods that are developed as we speak. So there are also quite a few papers on this prepared. So definitely the field is active. And of course, this is like work in progress. So we are not yet there. And maybe one word about the sharing of the models. Quite often when you prune the model or when you reduce the size of it, it's quite difficult, or the codes that are available on GitHub do not let you to share that easily. And in our solution, you need to just save one additional Python dict, which is decompose config, and send it to the person who will try to use your model along with the weights. And then just before loading the weights, you need to call one function from the library that will just decompose the model according to serialized recipe. So that is pretty straightforward, and so people who will use your model will do not need to know anything about the decomposition, SVD, and so on. Okay, so that's it. Let me summarize. So first of all, compressed models are useful, are nice, use them. They are cheaper to run, they are more convenient to deploy, and easy to store. So I think that's quite easily understandable. Then if you want to compress your models, there are a lot of methods, but I try to convince you that low-rank decomposition is one of the options to consider. We presented the application to large language models, to vision models. You can apply it also to other tasks and modalities. And also there is a package. You can use it and you can try to see if it works for you. Okay, that's it. Thank you very much.
Thank you. Great, thanks guys. All right, do we have questions? Yep.
Hi, thanks for the great talk. I have the question regarding the compression algorithm. You said that you decompose weights in the topological sort order of the network. And my question is, did you try changing this order, and did you see whether the change of this order affected the algorithm performance?
So there are two reasons why this happens. One is practical, the other is experimental. So the experimental one is that it seems to perform better. Like we can start from the first layer, and we can basically try to start from any layer, but we try just taking the first layers of the model, going in order and going like in the reverse order. So the reverse order seem to perform better, and from the practical perspective is you have to pre-compute these covariance matrices. And if you want to reuse them, if you want them not to change, going in the reverse order, you just make sure that the outputs at a particular layer just stay the same. So if you pre-computed these matrices, they're still valid for your model. And that's the practical reason. And this pre-computation saves up a lot of time. So without it, it would roughly take, I don't know, 4-8 times longer to run this, because you would have to compute them as you go. So but the experimental, let's say, rationale for this is not very well funded. There may be different, more optimal scenarios. We have to trade off some things as you go. So we decided to take this simple approach where we can reuse something that we have pre-computed before. Yeah, I hope this answers the question.
Okay, yeah, we see that the answer is Accepted. All right. Do we have more questions to our speakers?
Yeah, so you mentioned LoRa, and LoRa is useful when you have when you want to make your fine-tuning cheaper, and also if you want to prevent overfitting. But in this case, you already have relatively small neural network. That's should be already easy to train and also cheap to train. So how important is this LoRa application for fine-tuning?
Okay, so first of all, the LoRa is used only for language models, large language models, and for vision we just do the full fine tuning. And in the large language models, it's still a large model, maybe smaller than the previous one, but still LoRa saves a lot of time. Łukasz, do you have any extra insights? Yeah, so I believe if you want for practical applications like serious fine tuning, you could use you can use the full fine tuning also, and probably you would need also to have a better data set, yes, for this.
Okay, thanks.
Okay, thanks. Do we have more questions? All right. If there are no questions later, guys, will you stay with us for the after party?
Yes.
Okay, so we can ask your questions then. Okay, let's thank once again our speakers. Thank you, guys. And it's time for our third speaker, Ola Chrabrowa from Allegro.
Hello, everybody. My name is Aleksandra Chrabrowa, and I'm here to present you my work at machine learning research team in Allegro, and more precisely, dense retrieval for Allegro search engine. And for a quick start, I want to give you an introduction to our business scale and impact. So over 20 million internet users visit our site or mobile app every month, and this is almost 70% of Polish residents and 75% of all internet users in Poland. And the typical thing these people want to do is to search for something to buy, and Allegro users can select from over 500 million offers or 140 million products. And this difference between offers and products is when you, for example, multiple sellers can have multiple offers for one product, for example, for one model of an iPhone. And implementation of AI algorithms for this search engine translates into GMV growth directly, where GMV is gross merchandise value. It is the money that people buying something at Allegro pay to us. And current ML models implemented in production have resulted in over 1 billion Polish zlotys of incremented GMV attributed to these ML models. Okay, so as for the plan of the presentation, the first part will be an overview of machine learning in e-commerce search pipeline. It will be quite high level. I will compare dense and sparse retrievers, and I will show you how we come from ranking to the final listing. Then I will delve into our dense retriever model. I will tell you about training data and metrics. I will tell you about the two-tower architecture we use. I will tell you about contrastive learning we use. And I will show you some results from our experiments. And last but not least, I will tell you about serving our model, about FICE, approximate nearest neighbor search, and about a hybrid solution with sparse retriever. That's it. Okay, so as for the pipeline, here's the pipeline. So what happens when you type some query in the search box of Allegro? And this is the overview of our search pipeline. And I would like to say that this is an envisioned system, and this is a work in progress, as always in tech companies. But most of part of these systems are in some stage of deployment, and this envisioned system is compatible with current state-of-the-art research on this matter. And of course, a real system is also much complicated. And here I focus only on the ML part of the system. Okay, so each component of this search pipeline gradually processes a smaller number of items. And each of these components should work up to tens of milliseconds. We start with a dense or semantic retriever and sparse or lexical retriever. This is the first part of the system. And this is a high-level search among all products or offers with very high demands on the response time. And there is this older technology, which is called sparse or lexical retriever. And this is based on keyword search, and this is also called exact search. And of course, the main idea is that if we check for all the items that contain given words. Of course, there are some improvements to it, but the main idea stays the same. And the somewhat newer technology is semantic or dense retriever. And here we do not we do not do the keyword search. We do the search based on the similarity score between embeddings of the user query and of products in our database. And these embeddings are computed by a neural network by a specialized retriever model. And hybrid approach, combining results from the dense and sparse retriever, gives best results. Okay, so we are now past the retrieval step, but we can still do better. And we have a cascade of rankers, pre-ranking, re-ranking. And the main idea is that you want to sort the results and perhaps take only the top results and display them to the users. And each ranking step processes a narrower selection of items. And both textual and non-textual features, such as price, popularity, can be used. And there is one question that people often ask: why can't we use? Because there is some similarity score from the previous steps. Why can't we use this similarity score for ranking? And the answer is that if you don't have anything, you could use it, but you can get a lot of much better results if you have specialized models for ranking. And it is worth to know that at the last step of our ML pipeline, there is this ML Captain model, which dynamically computes the position of advertisements, which can be bought by the sellers, to find the right place for them based on how well they fit. Okay, and it took me about 5 minutes to go with you through all these steps, but in reality, it should happen in tens of milliseconds. And finally, I am able to present you the results of our search. Okay, so on to the dense retriever model. Our training data is based on our historical logs. There are pairs of query and product based on clicks from Allegro data. It means that we are looking at the situation when a user typed a query into the search box and then clicked on a product. Our test data sets are constructed in a similar way. As for metrics, we have for offline experiments, we use MRR, mean reciprocal rank, and we use recall. Recall is more directly reflects what we want to achieve, because recall measures out of for a given query, we have a set of ground truth relevant examples for these relevant items for this query, and we compute what percentage of relevant items was retrieved, and we take the mean for all queries. And of course, this recall is computed for a given k of top retrieved products, which can be, for example, 10 or 60 or 100. And MRR metric is a little bit more nuanced, because it takes into account the position of the relevant item on the list. And our final evaluations of our dense retrieval model are, of course, A/B tests in production setting. Okay, so onto the architecture. We use two-tower architecture, and we are basing it on this Q2Search paper by Facebook. And we have one tower of encoders for the user query, and we have second tower of encoders for the item or products. And we have each tower contains actually two encoders. One is ProdBird encoder. This is a BERT-based model trained on Allegro product data. So this model knows a lot about our products even before we start the training. And we also have a very simple model, which is a bag of embeddings. We take when we have some product or query, we split this into character trigrams, as depicted here. The idea for what are the character trigrams of word trigram, and for each of these trigrams, we train an embedding, and this is very simple, very shallow model. But added along this ProdBird, it gives some small but not non-negligible boost to our performance. And then we have query embedding and item embedding, and we compute cosine similarity. Okay. So why do we use two-tower architecture for retrieval? So there are two sides of this problem. We could use cross-encoder, like here, which jointly processes a query and product from the beginning. And it would have more capacity by design to process interactions between query and product. However, by encoder, like this two-tower model, allows to pre-compute a lot of things in production, and this is important. And as a side note, I cannot not mention Rocket QA paper, which gives us best of two worlds of cross-encoder and by-encoder training. Okay, so we are using contrastive learning during our training, and the main idea of contrastive learning is to we have query as our anchor, and we have a relevant product, for example, this pair of shoes. We have a non-relevant product, for example, this monitor. And during the training, we try to pull the embeddings of a relevant item closer to the anchor and push the embedding of irrelevant item farther from the anchor. And as a quick reminder, when we have, for example, during training, a batch size of, let's say, 3, the number of possible query and product pairs is 9, among which there are 3 positive pairs and 6 negative pairs. And this is important for our experiments. We investigated in practice the scaling law for our model with the batch size, and we found that it follows closely the linear scaling with the logarithm of the batch size. And so if you increase, for example, the batch size by twice, you increase recall by 2.5 percentage points, and you increase MRR by 1.5 percentage points. And of course, the main bottleneck for these large batch sizes is the GPU usage during the training process. And batch size used during training process does not affect the deployment of the model. And as a small side note, the fact that we are usually using a larger batch size that in the research papers on this topic means that sometimes when we come across a paper that proposes some method, it might happen that the improvement proposed by this method will not hold when we increase the batch size. Okay, and there is this second experiment I would like to tell you about. So there is this problem of hard negatives. So as you have seen on the previous picture, monitor was used as a negative example for the query about shoes. This was so-called random negative example. We have a random batch of examples during the training, and just random positive examples for other queries were considered negative examples for a given query. And perhaps these random negative examples, maybe they get too easy for the model as the training progresses. And here comes the idea of hard negatives. And we implemented the solution as proposed by a so-called STAR paper. The training process is as follows. First, we train our model with in-batch or random negative examples until it more or less converges, until the training is saturated. Then, as the second step, we compute hard negatives. For each query we want to use later in the training, we find top most similar products according to our previous version of the model. And by choosing some thresholds, we select some of these top examples as these hard negatives. And I would like to mention that this step is expensive in terms of computation, in particular time of computation, and we cannot do it too often. And then we take the weights of our model from the step 1, and we continue the contrastive training. However, we use hard negatives from this step 2. More precisely, for each query, we have an relevant item, and we have some number of hard negative examples. And these hard negatives examples for a given for this first query serve as random negatives for for example, the second query. So during the training, model has both random and hard negatives. And as remarks about our implementation, so there was some you have to choose wisely how you filter out the hard negatives based on the threshold. And of course, the idea of hard negatives is not new, but we chose this paper because we thought that it solves nicely some nuances about training stability. And in terms of improvement in the metrics, here is the improvement by quite a few percentage points. Okay, so I have concluded the part about our model, And I would like to tell you more about how it is served in production. And I would like to say that this is not the end of turning the model is not the end of the problems, because we have to serve it quickly in production under tens of milliseconds. And so it means it is best to pre-compute some things and not compute them online. By online, I mean computing something when user asks the query. So offline, we can pre-compute embeddings for all Allegro products, because we have a by-encoder two-tower model, and we can separately pre-compute embeddings for all products in Allegro database. Then, when user asks the query, we compute only one embedding for the user query. And now we have a task. We have one query embedding, and we have millions of products with the respective embeddings. And we want to find most similar product as measured by cosine similarity. And naive solution, which is exact nearest neighbor search, computing cosine similarity for all product embeddings would take too long and would be unfeasible for our business solution. And here comes approximate nearest neighbor search, which is typically implemented with FAIS library, although there are other libraries available. And again, we pre-compute some more things. Which takes hours, but then during the online computation, we have less to compute. And here is a general idea of ANN algorithms, although there are many other flavors of ANN algorithms, but let's focus on ones. We have our products and product embeddings. We cluster these embeddings with k-means, and now we have 5 clusters of products as depicted by different colors. We do exact search when we have a query embedding and want to find the most similar products. We do exact search among cluster centroids, and then we do exact search only among members of the most similar cluster. And this speeds up our computation. And this is also only a simple variant of ANN. And in practice, there is a lot of challenge to choose optimal FAIS configuration among many possible options. And it is also because you have to account for different, for the time of computation, for memory usage, for time of creating the index, and also for other practical problems, when you compute a cosine similarity between two embeddings, there is always some result, and you come with the problem of how to cut off the results, and we have found in particular the new method which precomputes, which selects the threshold individually for each query based on some drop or some knee in the data when the similarity drastically decreases. And I would like to spend more time on the question: why do we use hybrid approach? Why do we combine results from dense and sparse retriever? So first, I would like to say that adding dense retriever is a great improvement to the performance. However, we keep sparse retriever because it is very good for exact match queries. So dense retriever, so when we have a very simple query, when we want just to obtain to retrieve the products with exactly these keywords, it may be sometimes a little bit more difficult to get our dense retriever to do it than the lexical search. And And this lexical model is also more explainable to the user, and therefore it is easier to fix when something does not work. And last but not least, typically, this sparse model is fine-tuned with a lot of domain knowledge by experts, and it has been working in production for some time. So, as my personal opinion, when you come across some scientific literature about dense retrievers, and typically there is this comparison to BM25, which is an open source lexical retriever. And when you see that authors report some improvement over this BM25, you have to remember that in practice, your gap might be smaller, because BM25 is a vanilla sparse retriever. Okay, so that's it. I would like just to sum up that over 20 million Allegro users can select from 140 million products, and the retriever is the first high-level search for all products and offers. There are two types of retriever, dense and sparse. Sparse is based on keyword search, whereas dense is based on embeddings from neural networks. And our dense retriever model has two-tower architecture, uses our custom BERT model, and we trained in a contrastive way, and it benefits from large batch sizes and hard negatives. Thank you very much.
All right, thank you. Thanks, Ola. Do we have questions to our speaker? Okay.
Hi, thanks for presentation. Really liked it. I was wondering, how many clusters do you have for the 100 million products, like roughly? Is it 1,000, 100?
The k-means.
Yeah.
So for the FICE index, okay, so we follow this scaling law from the FICE documentation, and we found that actually it is good enough.
Thank you for the presentation. I was wondering, what are you exactly taking into account when you are calculating embeddings of the products? Just the description, or also the filters like, I don't know, the state of the product, the size of the screen, and so on?
Okay, so these experiments and these pictures showed only the product name, which is our main feature, but we are also using for example, description or parameters or other features.
Thank you.
Okay, thanks for the talk. So I have a question. You have this contrastive data set which you use to train the model. So if I understand correctly, the data for this model comes from like basically humans clicking on the outputs of this whole pipeline. So there is a risk that maybe if the model deteriorates, that also data deteriorates. Do you control it somehow? Do you find it to be a problem?
Okay, so I don't think that our click deteriorate. I think they're quite good and very useful data. However, it is a general truth that it is very hard to actually evaluate a retriever model in a bigger pipeline. First of all, because it is because it is a first step of the very large pipeline. So sometimes it is hard to say how other parts of a pipeline further influence it and shadow some improvements from it, maybe. And secondly, it is, as for training, this click-based data is very good, but for test part, sometimes it takes more consideration and effort to construct test sets. So I don't know if I answered your question exactly, but...
Okay. All right, accepted. That's okay. Good. Thanks. All right. Do we have more questions now? Okay.
So I don't remember it being mentioned, but have you tried or are you trying using embeddings based on different modalities for the product? So using some kind of multimodal
Yes, we are
models?
looking into it.
Yeah, okay.
But it was not covered in the presentation.
Okay, but it's not as we speak, like in production.
No, it's not.
Okay, fine.
There's one more question.
Thank you. I've got a question unrelated with your presentation, but inspired by your presentation. Have you been thinking in Allegro about implementing a natural language description-based search? So, for example, I can type in that I am looking for a gift for someone he likes color green and something like this. And have you been thinking, because I think it could be great?
Well, sharing my personal opinion, I think this is a great idea.
All right. Okay, good. More questions now? You can always ask our speaker. Will you stay with us for?
Sure.
Okay. So there will be opportunity to discuss this topic further during the networking part. So let's thank once again, Paula. Thank you. All right. So that was the last talk for today. Before we start networking part, just two announcements. The first one is that the next Warsaw.AI meetup will be probably in October this year, of course, but after the summer. But in June, we are planning to organize another event in collaboration with ML in PL conference, and it will be about the intersection of AI and education. So we haven't started promoting it yet, but stay tuned, and you can join our mailing list, newsletter, follow us on social media to just stay up to date, and there will be some announcements soon. All right, so with this, I would like to thank all of you for attention. Thank once again our speakers. Thanks for all the questions and answers, and we would like to invite you for the after party and networking part. So the food is already with us as usual in the fridge. So we just need some help to just distribute it to the tables. Thank you. Enjoy.